Good afternoon, class. We are looking at Chapter 7, Systems of Equations and Inequality, Section 7.6, Solving Systems with Gaussian Elimination. So we've covered a bunch of sections, systems of linear equations in 2 variables, 3 variables, nonlinear equations, matrices and matrix operations, and solving systems with Gaussian elimination. Now, the objectives are: write the augmented matrix of a system of equations, write the system of equations from an augmented matrix, perform row operations on a matrix, solve a system of linear equations using matrices. So what do we remember? Recall matrices and matrix operations. Matrices are classified by their dimensions, the number of rows and columns. A matrix with m rows and n columns has dimensions m by n. A square matrix has the same number of rows as columns. The dimension of a square matrix is n by n. A matrix with only 0 elements is called a zero matrix. The element of matrix minus A are the additive inverses of the elements of matrix A. Here's an example which has 1 and 2 rows, 1, 2, 3 columns. So we call it a 2 by 3 matrix. So here's the matrix operation is very similar to operations in algebra, operation of numbers. A plus 0 is 0 plus A equals A. 0 is the zero matrix. A plus minus A is A minus A equal to 0, which is the opposite matrix. A plus B is the same as B plus A. A plus B plus C is the same as A plus B plus C. In other words, the commutative and associative properties of numbers, now matrices. When it comes only to addition, summary of matrix addition or subtraction, if A and B are both m by n matrices, then the sum of A and B, namely A plus B, is a matrix obtained by adding corresponding entries of A and B. The difference of A and B, namely A minus B, is obtained by subtracting corresponding entries of A and B. The product of a scalar K, meaning a real number, and a matrix A is the matrix Ka, each of whose elements is K times the corresponding elements of A. The product of AB of an M by N matrix A and N by K matrix B is M by K matrix, and it's found as follows. To find the ith row, jth column element of AB, multiply each element in the ith row of A by the corresponding element in jth column of B. The sum of these products gives the element of row I, column J of AB. The product AB can be found only if the number of columns of A is the same as the number of rows of B. Notice this number must be the same as this number. The result will be this. The final product will have as many rows as A and as many columns as B. And we looked at the technology, the TI, for example, how to enter matrices. We use matrix editor. Matrix editor is found by pressing second and x to the power of -1. Use the arrow key to the right to edit the dimensions you want and press enter. Put all the entries using the arrow keys, press enter. I hope you remembered. You can go back to my recordings if you want. Now, 7.6, solving systems with Gaussian elimination. Matrices and technology. Matrix methods enables calculators and computers to efficiently handle and solve large systems of equations. Matrix row transformations, also known as matrix row operations, that would be an efficient implementation of echelon method is called. So here's an example of a system of equations. So A sub 1x plus B sub 1y plus C sub 1z equals D sub 1. And the second and the third equation where A sub 1, B sub 1, C sub 1, D sub 1, and the rest of them, they're all numbers. So we can just write these numbers together in the following manner. We don't write X, Y, Z, we just write the coefficients, these columns, and these are the rows. This is the coefficient matrix, and this is the constant matrix. This is called an augmented matrix, where each member of the array is called an element or entry. The rows of an augmented matrix can be treated just like the equation of a linear system. Okay. So whatever we do to an equation, we can do to matrices. For example, you can multiply this equation by any number, not zero, both sides. Then you're not changing the essence of the equation. The same thing happens here. So this part is called the coefficient matrix. And this one is called the constant matrix. Because we are putting the two together, it's called an augmented matrix. Augmented matrices are used to represent systems of linear equations. The system 2x plus 3y minus z equals 12, x minus 8y equals 16 is written as follows. So we want to write the augmented matrix. To do so, you make sure the x's, the y's, and the z's are lined up. So the first column would be 2 and 1. The second one would be 3 and minus 8. The third one is about z, minus 1, and I don't see any z's, 0. And the last column, which is the constant, is 12 and 16. Or you can say the first row is 2, 3, negative 1, 12. The second one is 1, minus 8. I don't have a z, 0, and 60. So this would be the augmented matrix, everybody. Again, pretty straightforward. Write the following system of equations as an augmented matrix. So we're going to start with this one. Make sure the x's and the y's are lined up, the constants. So if you go with the row, you go with 3, negative 2, and 3. The second row, negative 2, 1, negative 2. If you want to go with columns, 3 minus 2, minus 2, 1, 3 minus 2. No matter what, this would be the augmented matrix. This is the coefficient matrix, and this would be the constant. What about this one? If you want to go with the rows, 3, 4, minus 2, 9, negative 2, negative 1, 1, 0, 1. I don't see a y, 0, negative 6, 3. If you want to go with the column, x's, that's the first column, 3 minus 2, 1. The y's would be 4, negative 1, 0, and the z's, negative 2, positive 1, negative 6, and here's the last column. So that's what you write. So each column on the left, x, y, z, represents a different variable. So this is the x variable, this is the y variable, this is the v variable. And this would be the constant. And as I mentioned, this is called the coefficient matrix. Coefficient matrix. So it's pretty straightforward. So that would be the equal sign. the variables, and the constant. All right, we can go back from, okay, so write the system of equation that corresponds to each augmented matrix. So from this one, we want to go with the system. So this would be the x's, this would be the y's, this would be the constant. So let's just write this x and y. So that means 4x minus 5y equals 15. This means 7x plus 8y must be negative 9. For this one, we're going to write x, y, z. That means 2x, 0y, we don't have to write it, minus 6z is 3, minus 8x plus 7y plus 3z is 12, minus 5x plus 8y plus 4z must be negative 3. So this is how you write them. Matrix transformations. Row transformations resulting in a matrix of an equivalent system for an augmented matrix are, number one, any two rows may be interchanged. That means you're changing the equations in essence. Equation 1 becomes 2, 2 becomes 1, makes no difference, as an example. The elements of any row may be multiplied by a non-zero real number. I can't emphasize this enough, non-zero. Because 0 makes both sides 0. But if it's non-zero, you are in essence multiplying both sides of the equation by the same number. You're not changing the essence of the equation. Number 3, any row may be changed by adding to its elements a multiple of corresponding elements of another row. In other words, if you add one equation to the other one, both sides, it's fine. It's an acceptable operation. You may do so by adding a multiple of the equation to another one. It's in essence the same thing. Now, matrix methods to solve systems of linear equations. So what do we do to solve them? We go with REF, short for row echelon method. We apply row transformations to get ones along the main diagonal and zeros below the augmented matrix. Or REF, reduce row echelon method, apply row transformation to get ones along the diagonal and zeros both below and above the augmented matrix. What do we mean by that? We are going to look at examples. First, let's discuss those row operations we mentioned. Row operations are used on augmented matrix to solve the corresponding system of equations. So what row operations? Let's remind everybody what we just mentioned. Row operations, number one, interchange any two rows. For example, if this is the augmented matrix 4 minus 5, 15, 7, 8 minus 9, we can change these two. Remember, this represents an equation. This represents an equation. So this is equation 1, this is equation 2. If you interchange them, you're just saying equation 1 is now equation 2 and vice versa. That's the first one. So we're going to put this one in the first row, this one in the second row. And the way we do it, we write R sub 1 is being interchanged with R sub 2. So the first row becomes the second row. Again, you can do that with row operations. I can't emphasize this enough. It's not column operations, row operations. The second one, okay, so row 1 and row 2 were interchanged. The second one, we can replace a row by a non-zero multiple of that row. For example, if I write R sub 2 equals negative 2 R sub 2, that means the new row is multiplying the second one by number -2. So -2 times 7, -2 times 8, -2 times -9. That's the meaning of this, which of course doesn't change the first row, but the second becomes -14, -16, +18. So what are we doing? Every entry in row 2 was multiplied by -2. Replace a row by the sum of that row and a non-zero multiple of some other row. For example, what are we doing here? It says now R1, that means the new R1. So we're going to change this first row. How do we change it? We're going to multiply it by 4, and then we're going to add R2 to that. So what happens? This means 4 times 4 plus 7, minus 5 times 4 plus 8, 15 times 4 plus what number? -9. The second row, don't touch it. That's the meaning of it. So one more time. Multiply everything by 4 here and add the second row. That's the meaning of this. Take a look. 4R1 plus R2. Now, 4 times 4, 16 and 7 is 23. 4 times -5, -2 and 8 is -12. 4 times 15, 60 and -9 is +51. So what have we done? Every entry in row 1 was multiplied by 4 and then added to row 2. So row 2 was added to that. So then row 2 was added to that. All right. So that's the concept of row operations. The main reason for using a matrix to solve a system of equation is that it is more efficient notation and help us organize the mathematics. Here's an example for this augmented matrix. 1, 0, -5, 1, -5, 8, 0, 1, 4. If you want to read it column-wise, either way is fine. Find a row operation that would result in the entry in row 1, column 2, becoming a 0. So row 1, column 2. We want this one to change to 0. That's what the question is asking everybody. I hope you understand what they're asking us to do. So the question is, how do we do that? Well, if I want this to be 0, what can I add to it to make it 0? If I add 5 times this, that means I'm adding 5 times 1 to this, and I make it 0. So multiply the second row by 5 and add it to that. So we're going to write R1, that means the new R1, will be 5 times R2 plus R1. So 5 times this is 0 plus 1 doesn't change anything. So 5 times 0 plus 1. This one, 5 times 1 and -5. This is 5 times 4 plus 8. So notice the second row is not changing. So again, 5 times 0 plus 1, 5 times 1 minus 5, 5 times 4 plus 8. So this is 1. Now this is 0. That's what we wanted. This is 28. And the second row is unchanged. That's the idea, everybody. We are going to move on. Solving systems using matrices. This matrix is in echelon form. Why is that? A matrix is in row echelon form when the entry in row 1, column 1 is a 1 and zeros appear below it. So here's the very first entry and everything below it is 0. The first non-zero entry in each row after the first row is a 1. Zeros appear below it and it appears to the right of the first non-zero entry in any row. So the next row, the very first entry which is non-zero must be 1, which is the case, and below it is 0. Any rows that contain all zeros to the left of the vertical bar, this is the vertical bar, remember, this is the coefficient matrix, this is the constant matrix, we're talking about the coefficient matrix to the left of the vertical bar, appear at the bottom. So if they are all zeros, they must be at the bottom. So look at the main diagonal. This is called the main diagonal, and they must be all 1. So this one, everything underneath is 0. This one, everything underneath is 0, and this is 1. So if you look at the last row, the first entry, which is non-zero, is 1, which makes perfect sense. And that's the idea. We want to go with the augmented matrix, bring it to this format, which is called echelon form. And I hope you recognize if we go with x, y, z, this means z equals -3. So you have one of them and you can do the back substitution to solve. So let's look at a very simple example. We want to solve a system by the row echelon method. Ultimately, you can use a calculator, but I want you to see how we can set this up and move on. We can do this by hand if we have a system which is involved, meaning many variables and many equations. It makes it easier with the computer or a calculator. So first and foremost, let us write the augmented matrix here, which makes it 5, 2, 1, 2, -1, 4. So as I mentioned, this is called the coefficient matrix. This is called the constant matrix. Okay, so I wanted to make sure we know that. And what do we want to achieve? We want to put it in row echelon form. Remember, the row echelon form says the first entry we want it to 1. So we want the very first entry, we want 5 to change to 1. So what type of a row operation? Now, by the way, you can always use fractions. If you could, you try to avoid it, but either way is fine. For example, I have 2 ways to make 5 1. One is to multiply this row by 1/5 or divide it by 5. That's one way to do that. The other one is that if I multiply this row by 2 and subtract it from that also achieve that. So if I go with 1/5 of row 1 goes to row 1, see 1/5 of row 1 this is the new row 1. So this becomes 5/5, which is 1. This is 2/5. This is 1/5, and the second row doesn't change. Again, I could have said that row 1 minus 2, row 2 is the new row 1. 2 times of this one, if you subtract it, you get 1 here. And this way you avoid the fractions. Again, that's the idea. Now, the next thing that you have to do, you got to make sure if this is your first entry, everything underneath is 0. When I say everything underneath, there's only 1, but let's say there were more. You make this one 0, the next one, the next one. The first, you make everything 0 underneath this first entry. There's only one entry. I want to make this 0. That's what I want. So how do I make this 0? I can't multiply this by 0. It's unacceptable. Remember that. But I can add multiples of this row to this row. So if I multiply this one by 2 and subtract it from this, this becomes 0. In other words, negative 2 times R1 added to R2 and make it new R2. So multiply this one by negative 2 and add it to the second row, make it a new row. So the first row doesn't change. So the first row, you're going to write 1, 2 over 5, 1 over 5. What happens here, this becomes 0 because 2 times 1 subtracted from 2 is 0. Now, if you multiply this one by 2, you get 4 over 5. Subtracted from negative 1, you get negative 9 over 5. If you multiply this by 2, you get 2 over 5, subtracted from 4. So 4 minus 2 over 5. 4 is 20 over 5 minus 2 over 5 is 18 over 5. So again, multiply this by 2 and subtract it from this row. Again, 2 times 1 subtracted from 2 is 0. 2 times 2 over 5 is 4 over 5. Subtracted from negative 1, which is negative 5 over 5, makes it negative 9 over 5. This one, 2 over 5 subtracted from 4. So this is a 4 minus 2 over 5. 4 is 20 over 5 minus 2 over 5 is 18 over 5. What's the next one? We want to make this one 1. How do you make this one 1? Multiply everything by the reciprocal of that. That would be the fastest way. So the reciprocal of this number is minus 5 over 9. So minus 5 over 9 r sub 2 becomes the new r sub 2. So that means don't change that. And this one, I'm going to multiply it by this number. It's important to know, you worked very hard to change this to 0. You don't want to change that to anything other than 0. So whatever operation you do, make sure this doesn't change. So when I multiply minus 5 over 9 by 0, it doesn't change anything. That remains as 0. When I multiply it by this one, I get positive 1. When I multiply it by this one, 5 cancels out 5. I get minus 18 over 9, which is minus 2. Again, multiply minus 5 over 9 by this number, plus minus 5 over 9 by this number, gives you negative 2. What does it mean? This is the x column, this is the y column. This means x plus 2 over 5 times y equals 1 over 5. This means 0x, we don't have to write it, y equals negative 2, which means we have one of the solutions. Now we're going to do back substitution. We're going to replace this with negative 2, everybody. So we get x. Now negative 2 times 2 becomes minus 4 over 5 equals 1 over 5. This one moves, becomes plus 4 over 5 with 1 over 5 is 1. And you come up with the answer with the back substitution, 1 minus 2. What do you do next? Must check. We go back to the original equations. I'm going to quickly check this one. From now on, I'm going to leave it for you. X is 1, so 5. 2 times minus 2 is negative 4. 5 and negative 4, they add up to 1. 2 times 1 is 2. Minus 2 is plus 2, makes it 4. So that checks. So the beauty of math is you can check your work. Don't forget to check your work, class. I can't emphasize this enough. Now, as I mentioned, it is very easy to use technology. So we are looking at the same question, class. This is the same question, but this time we're going to use calculators. And I have shown you already how to use the matrix editor, okay? And I'm repeating it here for you so you can use that. So you choose whatever you want a matrix to be. In this case, you change it to 2 by 3. Class, you change it to 2 by 3. It's important to put it in a format that works, 2 by 3. And you put those numbers 5, 2, 1, 2, negative 1, 4. You put those numbers. Then you do the same thing, but this time instead of edit, you go to math. If you go to math now, see we have names, math, edit. Edit lets you change the size and put in the information. Now you go to math and you see those, we want REF. So we're going to use REF, row echelon form. REF of what? Well, since we call this AREF, matrix A. So how to solve a system by matrix? Row echelon form. 1, matrix editor found by pressing second x to the power of negative 1. 2, math. Then A, REF, put matrix A, note, pressing second x to the power of minus 1, enter, bring up matrix A and enter. So when you want to, after that, you have to go back to the names and bring up A. So REF matrix A has to be a matrix. So it gives you this one. And by the way, it may give you in decimal format, it may give you in a fraction format. But if you go to math and change it to fraction, it can change it to fraction. So this is changed to a fraction. And this may or may not be the way that you had it. Okay, it may be slightly different because row echelon form is not unique. However, we can do the next one that you can see here is our REF, okay, called reduced row echelon form. Matrix editor found by pressing second x to the power of negative 1, math, okay, or REF matrix A. And if you do that, it gives you this. First of all, when it comes to reduced echelon form, what it does, so 1, 0, then 1, and it makes this one also 0. Notice this is 2 over 5. Now, our REF makes this 0, and therefore, you don't have to do back substitution. This means y equals negative 2, because it's 0, x plus 1, y. This means 1x plus 0, y equals 1. So this gives you the answer, and as you recall, we had this previously. So when you do RREF, the last column is the solution, everybody. Solve a system by the row echelon form. So we have this one, x minus y plus 5 z equals minus 6, 3x plus 3y minus z equals 10, x plus 3y plus 2 z equals 5. And by now, everybody knows how to get the augmented matrix. So we have the augmented matrix, everybody. So take a look at that. And so what do? What is it that we want to achieve? We want the first entry to be 1. It is. We don't have to do anything. So this is given. If it wasn't, let's say for the sake of argument, this wasn't 1, but this was, so you could have interchanges. So the first entry must be 1. It is. We are in good shape. Then we want to make this 2 0. So the next step is to make this one 0 and make this one 0, both of them, not just one of them. So we can do it in one shot. Okay. So let's see how we do that. To make this one what you want, if you multiply this one by 3 and subtract it from row 2, and you call a new row 2, that will do the job. So negative 3 row 1 plus row 2 gives us the new row 2. The way we write it, negative 3 times the first row plus row 2. Now this is the new row 2. This is the new row, second row. Now, since you want this one to go 0, it's very simple. Subtract this from the third row. So you can say minus row 1 plus row 3 is the new row 3. So you are going to write the first row. You're not going to change anything. 1, negative 1, 5, minus 6. That's it. And you are changing these 2 to zeros because that's what you wanted. But to understand what happens, you're going to multiply this one by 3, right? So negative 3 times 1 is negative 3, and 3 is 0. Negative 3 times negative 1 is positive 3, and 3 is 6. Negative 3 times 5, negative 15, and negative 1 is negative 16. Negative 3 times negative 6, negative a positive 18, and 10 is 28. This one, simply put, subtract this one from this one. Subtract this from this one, you get 0. Subtract this one from this one, you get 4, because 3 minus 1. 2 minus 5, negative 3, 5 minus negative 6 makes it 11. So I'm assuming we can easily do this. What is the next one? This has to change to 1. So how do you change it to 1? One way is to multiply this one by 1, 6. So divide this second row by 6. Sometimes you want to avoid the fractions because they make it difficult at the end to solve, but that's fine. That is the fastest way. So the first row and the third row don't change. This one, 0 divided by 6 makes no difference, doesn't change. 6 becomes 1. Minus 16 over 6, or minus 8/3. 28 over 6, or 14/3. So we've divided this second row by number 6, and we got this new row. Okay, everybody? All right, what comes next? So we got 1, all of them is 0. 1, the one below must be 0. So we want to change this number 4 now to 0. That's our goal. How do we get that? Now, it's important to know, as you change this, okay, you don't want to change this one. You don't want to do an operation that can undo your hard work. So for the sake of argument, if I want to add multiples of the first row to the last one, this will undo this. So you can use the second row. That would be a smart one. In order to make this 4, if I multiply this one by 4 and subtract it from this one, makes this 0. In other words, negative 4 R2 plus R3 is the new R3. Negative 4 R2 plus R3. So what does it mean? Write this one unchanged, write this one unchanged. The first 2 rows, don't change them, just write them. The first 2 rows. Now we're going to work on this. Remember, this is 0, this becomes 0. Now multiply this one by negative 4. I want to make sure we understand what's happening. See, so we are going to multiply this one. I want to show you here, and then I'm going to erase it. I'm going to multiply this by negative 4. And then I'm going to add it to negative 3. Right, I want to show you what I'm doing. I'm multiplying this one by negative 4, and then I'm adding the negative 3. That's the idea. So we want to see what happens, what would be the new entry here. So we have 4 times 8, 32, divided by 3, minus 3 is 9/3, because we want to take a common denominator. So 32 minus 9 is 23/3. So this entry, everybody, again, this doesn't change, this doesn't change, this is 0, this changes to 0, and this changes to 23/3. I want to also show you number 11, what happens to number 11. Let me use this color. So what happens to number 11? We are going to multiply 14/3, okay, by -4, and then add 11 to it. So we have 56 negative thirds plus 11. 11 is 33/3. And we get negative 23/3. Negative 23/3. So I hope you see how this calculation comes about. The next step is to get rid of the 23/3, so divide by that. So this row multiplied by the reciprocal of that, 3/23. So if you want to make this 1, right? So you're going to multiply it by 3/23. When you do that, this becomes 1 and this becomes -1. The first and the second row are the same. The third one becomes 0, 0, 1, -1. And this is in row echelon form. The main diagonal is 1. Under this one is 0. Under this one is 0. And the very first non-zero entry is 1. And so what does this mean? X minus y plus 5z, because let me write x, y, z at top of it. X, y, z. So what does it mean? This means x minus y plus 5z equals -6. This is x, so 0x, so y minus 8/3 z equals 14/3. 0x, 0y, you don't have to write it. 1z, that means z equals -1, and therefore you have one of those. So you have z equals -1. Back substitution means you are going to plug in. You are going to plug in to find the y. I'm going to show you one of them, and I'm going to leave the third one for you. So if I put the -1 into this, I get y minus 8/3 times -1 is 14/3. And y is 14/3 minus 8/3, because this is plus 8/3, and that gives us 6/3, and that gives us 2. So we have z equals -1, y equals 2, and x is missing. So you put into the first equation x minus y, which is 2, plus 5 times z. That means -5, right? Because 5 times -1 equals -6. So I hope you see that you end up with 1. So so this results in x equals +1. So back substitution will give you 1, 2, -1. I'm going to clean up the mess because I need the space. You can work it out again. The way you work it out is very simple. This is -1, put it here, put z, and then put it in here, find the last variable missing. All right, so we have the answer, but let me quickly show you an easy way, of course, with the calculator. So you put matrix A, which means you put this augmented matrix, everybody. This augmented matrix, you put it into a calculator, and all you have to do, go with RREFA. It creates this one. Notice this is an identity matrix, by the way, and it's done. This is your solution. 1, 2, -1. Of course, it's a lot faster, but it's important to understand the concept, and with a little bit of a practice, you become comfortable with that. As long as you can do the raw operations on your own, then when it gets involved, you can always use a calculator. So that's the idea, okay? All right, solve a system by reduced row echelon form. So this is the system. We're going to write the augmented matrix. And you can write 1, 2, 3, 1, -1, 1, 1, 1, -2, 6, 5, 9. If you go or row wise, 1, 1, 1, 1, 1, 6, 2, -1, 1, 5, 3, +1, -2, 9. As long as you just write the coefficients and the constant, put them together, and of course 1, 2, 3, 1, 2, 3, 4, 3 by 4. And I don't expect you, after you do a couple of examples, I don't expect you to do more by hand. You can put it into a calculator. First, matrix A has to be 3 by 4. You put the information. Then here's a matrix A, the augmented matrix. You do RREF, and it gives you this matrix, meaning what? This last column is the solution. X is 3, Y is 2, Z is 1. It's very straightforward, class. We want to solve this by reduced row echelon form. We are going to write the augmented matrix again. Again, 1, 3, 2, 2, 2, 3, 1, 2, 1, 30, 56, 44. I went column wise, but you can go with row 1, 2, 1, 30, 3, 2, 2, 56, 2, 3, 1, 40. So that is the augmented matrix. You put that into a calculator. By now, you know how to do that. And when you do the RREF, it results in this. And I'm going to rewrite this so it makes it easier. So you put it into a calculator, it results in this. This is the solution. Because this is an identity. All of them are 1. Notice that the main diagonal is 1. So this means X is 8. This means Y is 6. That means Z is 10. And you're done. Again, extremely simple, class. Let's say we have another system we want to do by row echelon form. So we're going to write the augmented matrix for this one. 1, 1, 2, 2, -2, 4, 1, 3, 2, 4, 1, 9. If you want to go with the row 1, 2, 1, 4, 1, -2, 3, 1, 2, 4, 2, 9, and here's your augmented matrix. It's very important. If any variable is missing, that means you have the placeholder 0. Don't forget that. So we're going to do we're going to do the REF. Okay. I want to show you something if we were to do this by hand. if you multiply, so this one is 1, this one is 1. If you multiply the first row by 2 and subtract it from this one, something very interesting happens. That's why I wanted you to see this by hand. So if we don't change those two and you multiply this one by 2, you get 2 subtract from 2 is 0. You multiply this by 2, you get 4 subtracted from this, you get 0. You multiply this by 2, you get 2 subtracted from 2, you get 0. You multiply this by 2, you get 8. Subtracted from 9, you get 1. So all of them are zeros except the last enter. And this is the idea that I wanted you to see. When all entries are zeros, except the last one. The last one is something. Doesn't matter what it is. It's 1 or anything else. Let's see the meaning of that. This is x, y, z. 0x plus 0y plus 0z. That means 0 equals 1. That's a false statement. The final row indicates that the system is inconsistent and has solution set phi, no solutions. This is phi, which represents an empty set. So if all entries to the left of this line is zeros, they are all zeros. And to the right is not. Doesn't have to be 1, any number. Remember, this means 0 equals this number, which can't be. If you go with the technology and you do REF, it results in the same thing. If you do REF, again, the last row, in this case, the last row, in this case, the last row, indicate what you are looking for. Even REF will show you that there is no solutions. Again, meaning what? All entries are zeros except the last. So hopefully we are comfortable with technology. That's not a big deal. What about this one? We want to write the augmented matrix again. So let's write down 2, 1, 4, minus 5, 4, minus 10, 3, negative 2, 6, 1, 8, 2. And again, you can put it into technology. I want to show you something. And this is, sometimes you can notice by looking at it. If we multiply this one by 2 and subtract it from the last column, so minus 2R1 plus R3 becomes the new R3. Let's see what happens. I'm going to multiply this one by 2. I get 4. Subtracted from 4, 0. I'm going to multiply this one by 2. I get negative 10. Subtracted from negative 10, I get 0. Multiply this by 2, 6. Subtracted from 6 is 0. Multiplied by 2 is 2. Subtracted from 2 is 0. So the last row, all of them become zeros. Now something different happens. Again, you could put it into technology, but I want to make a point here, and this is extremely important. This means 0x plus 0y plus 0z is equal to 0. In other words, 0 equals 0, which is a true statement. And that means we have a dependent system. So the final row of zeros indicates that the system has dependent equations. The first 2 rows represent the system. Now, this one, the first 2, we can write as 2x minus 5. Let me just write x, y, z, so you remember that this is x, y, z columns, right? So this means 2x minus 5y plus 3z is 1. This means 1x or simply x plus 4y minus 2z equals 8. So that means you want to solve that. But 2 equations, 3 unknowns, that has infinitely many solutions. That is a dependent system, and that's the concept, everybody. Let's look at it and see what happens. So we are dealing with this system we are going to solve. And we can solve it again with the augmented matrix. Now the new augmented matrix is 2, 1, negative 5, 4, 3, negative 2, 1, 8. You can go with the augmented matrix. And remember, the very first thing is that we want a 1 here. And since the second row has the 1 as the first entry, just change these two. It's like changing these two equations. So row 1 goes to row 2. That's the idea. So interchange these two rows. So this becomes the first row, this becomes the second row. That's the meaning of R1 with double arrows R2. That means change the rows. And remember, the next thing is to make this guy 0. So the next thing is to change 2 to 0. So how do we do that? If we multiply this by 2 and subtract it from here, that means minus 2R1 plus R2 becomes a new R2. See, negative 2 times R1 plus R2, it goes to R2 again. That means this is the new R2. So the first line, the first row doesn't change. Now, multiply this one by 2, subtract it from this, you get 0. Multiply this one by 2, 8. Subtract it from negative 5, you get negative 13. Subtract this by 2, negative 4. Subtract it from 3, that means add 4, you get 7. Multiply by 2, 16. Subtract it from 1, you get negative 15. So we got those. The next one is to make this guy 1. So divide by negative 13. The fastest way would be to divide this by negative 13, or negative 1 over 13 times R2 is the new R2. So the first line doesn't change. The second line 0. Remember, you don't want to change that, and it doesn't change anything. This becomes positive 1 because this is negative. This becomes negative 7 over 13. This becomes positive 15 over 13. And there's nothing else you can do. It's in row echelon form. You could go with reduced row echelon form. You can multiply this by 4 and subtract it for this one. This becomes 0, and it makes it a tad easier, but that's another step of row transformation. Just the way it is, I'm going to put X, the columns X, Y, Z. Therefore, we have X plus 4y minus 2z equals 8. This is 0x, so you don't have to write it. Y minus 7 over 13z equals 15/3. Now, this is the equation you're supposed to solve. All right. So that means we're going to write this as a function of z. The last variable is z. And so we're going to make this a function of z by moving this to the right. If you move this to the right, you get y equals 15 over 13 plus this. Now, if you put this in here, okay, you replace the y with this, then you can find x as a function of z. So let's put this in here, the first equation. So x plus 4y minus 2z becomes x plus 4 times this expression minus 2z equals 8. So let's work on this. 4 times 15 is 16 over 13. 4 times 7, 28 over 13z. So we're going to write it in this fashion. X doesn't change, minus 2z doesn't change, 8 doesn't change. First and foremost, this one is negative 26 over 13z, which gives this one as 2 over 13z. Okay. And then you have to move this one and 8 minus 60 over 13. 8 times 13 is 104 minus 60 makes it 44 over 13. I hope this is 44 over 13. And so what happens is x equals 44 over 13, and 2 over 13 z goes to the other side, becomes negative. And now here's what you have. This is the value of x. 44 minus 2z over 13, they have the same denominator. This is the value of y, 15 plus 7z over 13, and z. This is the way you write a system of equations, the solution to a system of equations when it's dependent and it has infinitely many solutions.